Hi friends, this is Mr. Zarzak, and in this screencast we're going to apply equations of motions to solve some example problems, and we're also going to derive a new equation algebraically. So let's get to it. Alright, over on the left I have the formulas that we have available in our toolkit so far for kinematics or motion, and we're going to work some example problems. Alright, so the key with this is to identify knowns and unknowns, and you pick the right equation to get the answer that you need. So it's really a matter of reading comprehension and the right tool for the right job. All right, so a rocket travels 10 kilometers in 22 seconds. So looking at kilometers, which is a unit of distance or displacement, and 22 seconds. Seconds is a unit of time. So the first equation on the board over here seems to be appropriate. I could compute the velocity in kilometers per second. However, I'm going to take and put the 10 kilometers into standard units of meters. All right, so in this class, we like to use a factor unit label method, which just says that if we want to find a distance in meters from kilometers, okay, we take the number, write it as a ratio, and then the identity is written as a ratio as well. So for every 1 kilometer, there's 1,000 meters. Okay, and so you see that we call this factor unit labels. So we're factoring out units, okay, by applying this method. Kilometers in numerator and denominator factors out, and my answer is going to be in meters. So then D is 1,000 times 10, so I got 10,000 meters, commas appreciated. Okay, and then once I have that value, all right, then I can just apply my average velocity is equal to the change in D over the change in T. All right, so if we start at 0 meters, we'll just use it as a reference. We go with this 10 kilometers or 10,000 meters. So our 10,000 meters is our change in D. Okay, and it takes 22 seconds. So think we start the stopwatch at time 0 and we end it 22 seconds later. And in that time, we've traveled this 10,000 meters in a time of 22 seconds. All right, so I could take and plug that into my calculator. All right, I've already done so to save some time. You get 454 meters per second. All right. General rule of thumb with this is a WebAssign question, just to be safe. If you got a non-repeating decimal for the answer, save 3 spots after the decimal point and do your rounding there. And that'll pretty much guarantee you for the entire year that you won't get any rounding errors on WebAssign. Okay. All right, moving right along. Okay, so we've got a car traveling down Crescent at 20 kilometers an hour. It slams on the brakes and stops in 10 seconds. What is its acceleration? Okay, so it's traveling down Crescent at 20 kilometers an hour. All right, so this is how fast? All right, so I got this 20 kilometers per hour. All right, it slams on the brakes and stops. Okay, so to stop, that is a velocity. It's a velocity of 0. Okay, it's a way of describing motion. All right. And it does so in 10 seconds. So I've got a time as well. All right, so time is 10 seconds. Okay, the reason I didn't put the units on that second velocity is because, well, the time is in seconds and the velocity is in kilometers per hour. So if we're going to compute the acceleration, all right, we need to have the units to be in the same base. We can't mix hours and seconds, all right? Standard SI units is meters per second. So I'm just going to go ahead and take this velocity and convert it. Before I do, though, which velocity is which? All right, well, it is going 20 kilometers an hour, and it slams on the brakes and stops. So this 20 kilometers per hour is my initial velocity. Okay, stops at the end, at the final velocity, just 0. Okay, so let's go ahead and convert 20 kilometers per hour into meters per second. Okay, so again, I'm going to use that factor unit label method. So for 20 kilometers per hour. All right, so just like before, all right, 1 kilometer is equivalent to 1,000 meters. All right, and I'm just going to take care of the time part too and just do this all in one conversion. All right, so I have hours in the numerator or the denominator of 20 kilometers per hour, so I need hours in the numerator up here, so we factor it out. And there are 60 times 60, or 3,600 seconds in an hour. Okay, careful on that. If I had a nickel for every time a student told me that there were 60 seconds in an hour, all right, well, I would not be a rich man, but I would have a lot of nickels. Okay, so I just an easy mistake to make. If you need to do it in 2 steps and go hours to minutes and minutes to seconds, by all means, go ahead. You can certainly do that. All right. And when you do that conversion, all right, you should find that this velocity is 5.556 meters per second. All right. So anyway, so once I have this, so what I'm really looking at is I have an initial velocity, a final velocity, a time, and I'm asked to find an acceleration. All right, and so really number 2 on the list here is the most appropriate. All right, so acceleration is equal to the change in velocity with respect to the change in time. All right, and so if I go ahead and sub in the change in velocity, that's always, 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 no exceptions, never. It's always final minus initial, final minus initial. Okay, so my final velocity is 0 meters per second. My initial was that 5.556 meters per second. Okay, and it takes a time of 10 seconds to do that. All right, so if I go and plug away, I'm shifting the decimal point and carrying the negative. All right, again, 3 decimals would be plenty. So if you wanted to do this final rounding flow besides just 3 decimals instead of 4, you could, or you could just put the 4th in. Sort of up to you. You get this negative 0.5556 meters per second squared. Okay, the fact that you have a negative sign with the acceleration, it really just means that in this case you're slowing down. So your initial velocity was this 5.556 meters per second. Okay, well that number does have a sign. We typically don't write the positive out in front of the numbers. Okay, it's implied. So the initial velocity and the acceleration, okay, are going in opposite directions. So like the initial velocity is forward, the acceleration is backwards. Okay, and the forward and backwards part, I don't know which way that is, but they're opposites. Okay, they're opposite directions within a dimension, and the consequence of having a velocity and an acceleration in opposite directions is you slow down. If velocity and acceleration are in the same direction, you speed up. All right. All right, moving right along. A car is traveling down Crescent at 20 kilometers per hour, slams on the brakes and stops in 10 seconds. What is the average velocity? Okay, so since I'm computing average velocity, all right, well, I've got that same initial velocity of 20 kilometers per hour here and the same stop, so final velocity of 0. Okay, I do have the time. Okay, but for the average velocity, I'm actually going to use this right here. Okay, I don't need the time. All right, so sometimes we're going to get problems where there's extraneous information that isn't necessarily used to compute what we're after. All right, we take what we want and we leave the rest. As far as the 20 kilometers an hour, all right, well, because the time frame is still in 10 seconds, okay, we would want to convert that value into meters per second. Luckily, we already did. Okay, and if you do this conversion like in the previous problem, so like if this was part of a set, right, and this is part of a set, like the first question up here is about the car is what's the acceleration? Okay, maybe this would be like part B of the question. You don't need to show the work for the conversion again. Now you do need to show it the first time, but once you have it, okay, you don't need to do it again. All right, what is that? 5.556. So 5.556 meters per second. Okay, and again, you don't need to show the work twice. Once is enough. All right, so once we have it, no problem to compute the average velocity. All right, we just take the initial plus the final, and we divide by 2. So average velocity is 5.556 meters per second plus final velocity, which is stop. Okay, divided by 2. All right, and so that average velocity is, what is that? That's 2.7, it's roughly 2.78 meters per second. Okay. All right, moving right along. If a sports car has an acceleration of 20 meters per second squared, how long does it take to go from 15 meters per second to 80 meters per second? All right, so we've got an acceleration of 20 meters per second squared. All right, we're being asked how long does it take, so that means that my unknown here is the time. All right, to go from 15 meters per second to 80 meters per second. So looking at the units of meters per second, that tells me that these are both velocities. And since it's phrased from to, that means that the 15 meters per second is my initial, and the 80 meters per second is my final. All right. Notice that the acceleration and then the initial velocity both have the same sign. They're both positive numbers, and so the consequence of that is that we speed up. We go from 15 meters per second up to 80 meters per second. All right. For this, I'm going to use the instantaneous velocity equation, also known as ultra mega 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 equation number 1. So Vf equals Vi plus At. All right. And I am going to use it to solve for the time. Okay, so you can sub numbers and do algebra, or you can do the algebra and sub numbers. I think it's a good habit to kind of push yourself into, whenever you can, solve algebraically first and then plug and chug. Simply because as time goes on, all right, the level of difficulty and length of problems is going to become greater. And so you're just kind of doing yourself a favor of trying to work through and get an algebraic solution whenever you can. I know that's not typical for most of us. It's a habit that you kind of have to break about going and plugging in numbers initially. But it is worth it to do. Let's see, so I have, what is this? This is 65 over 20. Okay, just so you can see it, if you take meters per second divided by meters per second squared up, you're not going to be asked to show this on a test. The numerical value, we just plug it into a calculator, and it comes out to 3.25. Okay, we know that we're solving for a time, so we know the answer is seconds. So just so that you can see it work out with the units, all right, instead of dividing units by units, we multiply by reciprocals. That's really the easiest way to see what's going on. So if I take meters per second and I multiply that by the reciprocal of meters per second squared, so second squared over meter, okay, we see how the meters factors out, and then one of the seconds does too. And so we do the time, the unit of the time really is seconds here. It does work out, so that's kind of nice. Moving right along. Okay, if a ball is thrown straight up at 100 meters per second, what is the height after 5 seconds? The initial conditions in this aren't so realistic, so it says it's thrown. I'm not really sure what's doing the throwing. 100 meters per second is roughly 220 miles an hour, so whoever or whatever is doing the throwing has quite the arm. So anyways, we can still solve it though. All right. We've got, let's see, thrown straight at 100 meters per second. So this is my initial velocity, so 100 meters per second. Okay, and it says, what is the height? So height is a displacement in the upward direction, so it's still just a displacement. That's our unknown. After a time of 5 seconds. All right. So in order to do this, we're actually going to use ultra mega 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 equation number 2. And you see that in order to solve it, we've got the initial velocity, we've got the time, and it's the same time in the first term and the second term in the problem. Okay, but the acceleration is not stated explicitly in the problem, but it can be implied. See, when something is in the air, okay, it undergoes uniform acceleration that comes from gravity. Now, what exactly gravity is, okay, we'll delve into that deeper throughout the semester, but for the time being, we can look at gravity in terms of what it does, which is cause things to fall downward. As they do so, as things fall downward, they don't fall at a constant speed. They fall at an accelerated rate of motion, so they speed up as they fall downwards. This is the reason why if you jumped off your bed onto the floor, okay, you'd probably be all right, but if you jumped off, the roof of your house, probably not so much. And don't try that at home. Okay, the reason that jumping off your roof is more dangerous is because, well, you're in the air for longer, which means that you are going to speed up more in the process of falling to the ground. So you hit the ground with a faster speed, okay, so that's going to cause more damage to you. All right, we'll get into more of the physics of that later. You've read the chapter by now Okay, so you have seen this, I should hope, that the accepted value for the acceleration of gravity near Earth's surface is 9.8 meters per second squared, and gravity points down. So the way that we would distinguish the direction is with the sign of our values. So my initial velocity is 100 meters per second. That's a positive number. Even if we don't write the little plus sign, that's implied. So the way that we would show that gravity points downwards is with a negative sign. Okay, a physicist would read that as 9.8 meters per second squared down. That's what the negative is. All right, so now I have everything I need, all right, in order to solve using this ultra mega equation number 2. So VIT plus 1/2 AT squared. Okay, by initial velocity 100 meters per second. Okay, 5 seconds later, all right, when gravity is causing the ball to accelerate downwards at 9.8 meters per second squared for a time of 5 seconds squared. And again, that's the same time for both t's in this equation. So let's see. So I got 500 all right, meters. Oh, I forgot my little negative sign. Excuse me up there. Let's see. Half of 9.8 is 4.9. 5 squared is 25. 25 times 4.9 is 245. Cut that in half, and that's, what is that, 122 and a half? Yeah, so minus 122.5 meters. So we get this 377.5 meters. All right. Moving right along. If a ball is dropped 10 meters, how fast is it traveling when it hits the ground? All right. So if a ball is dropped, that word dropped, okay, that's another word that we can imply some information from. Pardon me, dropped is very different than thrown or kicked or launched or fired. Dropped implies an initial velocity of 0. All right. We let it fall downwards 10 meters. Okay, so meters, that's a displacement. All right. It says here, how fast is it traveling when it hits the ground? So we're looking for Vf, that's our unknown. All right. And so we want to know how fast it's traveling when it hits the ground, just like the previous problem. Okay, once it's in the air, okay, it experiences a uniform acceleration due to gravity that has a value of 9.8 meters per second squared near Earth's surface. Now, gravity points downwards, okay, so in the previous problem, we signified that with a negative sign. And the reason that we made that choice was because, well, if I scroll back up here, my initial velocity in this problem was positive, okay? Well, here my initial velocity is 0, okay? It's not positive or negative, it's just 0. Okay, so there's really nothing that distinguishes positive, negative in terms of motion. If I look at displacement, okay, I wrote down 10 meters, okay, but it's dropped, so that 10 meters is downwards, all right? And so I have a couple of options here, all right? I have to make a choice in my positive direction, okay? If I choose upwards as my positive direction, okay, well, that means that if the ball falls 10 meters downwards, that's a negative displacement. Remember, in all these equations, the d is displacement, which is distance with the direction. Okay, and so if the ball moves downwards, it's going to move 10 meters down. We would show that with a negative sign. And the acceleration is downwards as well, so that would have a negative sign. Now, that's a choice that we make. We could also choose, because all the motion in this problem is downward, we could also make the choice that the downward direction is going to be our positive direction. Okay, and it's really up to us. We get to set the rule, and as long as we stick to the rule that we established, we can do this. I'm going to keep everything positive because everything's moving downward, and I know that is a little bit uncomfortable for some of you guys. All right, and then I'll show you what happens with the problem if we switch our convention as well, okay, because the physics still works out. All right, in order to do this, to get the final velocity, well, I don't have any equation that relates these 4 variables together to get the final velocity, okay, and so there's actually an intermediary step. All right, I'm going to apply ultra mega equation number 2 in order to solve for the time, okay? When we are describing events that pertain to motion, okay, Well, really, that is a description of motion that occurs in reality. And in reality, time has to pass for change to occur. And so, for a lot of physics problems, okay, the time frame is really important. If we don't have it, very often we have to solve for it. Okay, and that's exactly what we're going to do here. So, if I take this d equals VIT plus 1/2 AT squared, all right, well, my initial velocity here is 0, which means that any number times 0 is 0. So this first term in the equation factors out, and I'm left with d equals 1/2 AT squared. Okay, and if to solve for the time, I'm going to do a little bit of algebra. And again, I could sub in numbers first, but I think it's just kind of good for you to see this done algebraically and to try to force yourself to get in the habit where, if it's possible, get an algebraic solution first. All right, and then last but not least, I'm going to take the square root. Okay, let me clean this up a little bit. All right, so we've got the time is equal to the square root of 2d over a, where everything is underneath the square root sign. Okay, so if I take and I sub in my values, all right, so what do we got here? We got 2 times the displacement of 10 meters. All right, I should extend that down a little bit, divided by the acceleration of gravity, 9.8 meters per second squared. Okay, and so the time frame works out to be right around 1.4 seconds. All right, so it'll be 20 over 9.8 square rooted. Notice that there's, because I've chosen down as the positive direction, okay, underneath the radical here, I've got a positive 10 meters and I got a positive 9.8 meters per second squared. What if I had made a different choice? Okay, what if instead of down, okay, I had said I want to make up my positive direction? Okay, well, if I had done that, gravity would have a negative sign, but so would the displacement, because that displacement is downward. In which case, when I subbed in my numbers here, I'd be multiplying 2 times negative 10 divided by negative 9.8, in which case the negative signs factor out, and I still get the same time. Okay, and so it's just kind of neat to see, and that tells us that, you know, the physics equations are valid no matter which way we reference positives and negatives, and that's a good thing. Okay, once I've got this time, okay, I can now go and finish the problem by selecting ultra mega 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 equation number 1. So VF equals VI plus AT. All right, this thing is dropped. The ball is dropped, so my initial velocity is still 0. Okay, but now I can solve. All right, the acceleration as the ball falls is still due to gravity. All right, my time frame of 1.4 seconds. Multiply those two things together, and I get 13.7 meters per second. Okay, this number has a sign. This is a positive number. Okay, and because we have established that for this problem, we've chosen down as the positive direction because this has a positive sign out in front of it. The velocity is 13.7 meters per second down. All right. Again, if we had chosen to reference the other direction, if we had made up the positive direction, okay, in which case the displacement would be negative because the ball falls down. The acceleration of gravity points downwards because things fall downwards, not upwards. Okay, so we would sub in the negatives here. We still get the 1.4 seconds for time. Time is a scalar quantity. It has no direction. There's only one direction for time. Okay, in which case, if I had chosen this as my reference, okay, I'd plug in a negative for gravity, and I would get a negative 13.7 meters per second. And by my convention of setting upwards to positive, that would still mean that the ball is moving at 13.7 meters per second down. One last little point about this problem. Okay, it says if a ball is dropped 10 meters, how fast is it traveling when it hits the ground? A very common error, okay, conceptual error, is that when the ball hits the ground, it moves with a speed of 0. Okay, and that is a mistake you do not want to make. What we are saying with problems like this is that at the instant, okay, that it makes contact with the ground, It has a speed, an impact speed of 13.7 meters per second. Once it hits the ground, what it does, we do not know. Maybe it does stop, maybe it bounces, maybe it breaks into a zillion little pieces that go in all different directions. We have entire units of physics that are dedicated to what happens upon impact between two objects. Okay, that will come later. All right, when we say when it hits the ground, we're talking about that instant. Okay, and an instant is a length of time of 0 seconds. It's right when it makes contact, how fast is it going? All right, another way you can think about this, all right, is if I took a bowling ball and I dropped it on your head, which of course I would never do, all right, if you tell me that it hits your head with a speed of 0 meters per second, well, that means that I could drop it off of a 10-story building, and when it would impact your head, it would reach you with a speed of 0, in which case you wouldn't get hurt. You gonna try that demo? Because I'm not, okay? That's the point. All right, so watch out for that. It's an easy pitfall. All right, that was kind of a lot of work to do that. All right, I wish there was an easier way, and luckily there is. Okay, we can take ultra mega 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 equation 1 and 2, and we can combine them to eliminate the need to solve for the time. Okay, so this is kind of a cool little trick. All right, so what I'm going to do here is I'm going to take ultra mega mega equation number 1, okay, and I'm going to manipulate it algebraically. All right, so first thing I'm going to do is I am going to subtract over the initial velocity from the final velocity. So VF minus VI is equal to AT. All right, and then I'm going to take and divide out the acceleration. All right, so that I can write this in terms of time. So time is equal to VF minus VI over A. Let's make that a little bit cleaner. Okay. All right, best I can do. All right. In ultra mega 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 equation 2, I have time, and I also have time squared. Okay, so I'm going to do another little trick where I write this expression of VF minus V over A in terms of time squared. So what I do to one side of the equation, I do to the other. Okay, so VF minus VI. Okay, I'm going to square the numerator, and I'm going to square the denominator. Okay, and the reason I'm doing this is going to allow me to sub these two little expressions, this one and this one, into ultra mega 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 equation number 2. So watch what happens, okay? All right, D is equal to VI times T, all right, where T is this VF minus VI over A, so VIT plus 1/2 times A times T squared, and instead of writing T squared, I'm going to write in this expression VF minus VI squared over A squared. Okay, and so I've rewritten ultra mega 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 equation 2 in a manner where there's no time. All right, now this is pretty messy, but it cleans up pretty nicely if I'm willing to sit and do the algebra. So see there, I can factor out an A. Now what's nice about this is that leaves me with an acceleration in the denominator of both of these terms. Okay, and so what I'm going to do is I'm going to throw this in brackets. Okay, and I'm going to multiply the entire expression by A. And what I do to one side, I must do to the other. Okay, and there's also this 1/2 that's sitting in here. Okay, and so I don't want to deal with the fraction. So to get rid of the fraction, I'm going to take and multiply the entire expression times 2. Okay, to eliminate that fraction. All right, so let me take and distribute this out. So left side of the equation, I have this 2AD. All right, the accelerations now completely factor out. Okay, so I'm really just carrying and distributing the 2 through this. So I wind up with, let's see, so I have 2 times VI times quantity VF minus VI. Okay, plus, let's see, so the 2 and the 1/2 factor out, so I'm just left with VF minus VI squared. Okay, so that's a little cleaner. We can do better. We're not done yet. We're going to do a little bit more algebra. I promise this will be worth it in the end, and I won't ask you to do this derivation. I'm taking care of it, so once we have the tool, we can use it. Okay, so let's go ahead and finish this up. All right, so I have 2vi. I'm going to distribute, so vi vf minus 2vi times vi, so 2vi squared. All right, in the parentheses, I'm going to FOIL this out. So this is vf squared. So I would have minus vi vf and minus vi vf, so minus 2 v f vi, like this. Excuse me, 2. That's commutative. It doesn't really matter, but all right. And then last times last, so that winds up being a positive vi squared. Okay, so if I look at what I have here, all right, so I've got a minus 2vi vf and a positive 2vi vf. So those two just cancel each other out. And let's see, I also have a minus 2vi squared and a positive vi squared. So minus 2 plus 1, so that's just 1 vi squared negative. All right, so 2ad is equal to negative vi squared plus vf squared. Okay, so we're getting a little cleaner. And traditionally, we write this in terms of vf squared. Okay, so I'm going to add over the vi squared to the left side of the equation. So I got vi squared plus 2ad is equal to vf squared. All right, and then just for notation purposes, I'm just going to flip this around on itself. So I got vf squared is equal to vi squared plus 2ad. All right, this right here, this is that equation I said that we were going to derive at the beginning of the video. Okay, we call this the timeless equation because, well, it relates initial velocity, final velocity, acceleration, and displacement without having to know the time. There's another name that a student came up with a number of years ago. Sometimes we refer to this as the love equation. Okay, why? Because, well, as everyone knows, love is timeless. Boom. If I go back to that problem that I solved with the ball being dropped 10 meters, okay, the algebra was kind of messy, and again, I'm not going to ask you to do it, but once we have the tool, once we have the timeless equation, look at what happens to this problem. So it's dropped 0 meters per second. Moves downward at displacement 10 meters. Why? Gravity. How fast is it traveling when it hits the ground? I like that. Use the timeless equation, vf squared equals vi squared plus 2ad. Throw that in your calculator and you'll get that same 13.7 meters per second. Now, one little caveat about the timeless equation, okay? Because it's set up for vf squared, we have to take the square root. If we're in math class, I know they're a little bit more strict about the notation of when you take the square root, the solution being plus or minus the answer. Okay, and that's still true here. What the timeless allows us to do is to compute the magnitude of the final velocity. Now, the magnitude of velocity, that's just a fancy way of saying the speed. This equation allows us to know the speed, but not the direction. See, I chose the same reference I did in the previous problem where I said down was positive. Okay, well, if I chose up as positive instead, all right, that would make this a negative 10, and this would make this a negative 9.8. In terms of computing the value, okay, well, I'd put those negatives in there and they would factor out, but I would get a positive answer, all right? But the ball's moving downwards. Okay, so that's my word of caution with the timeless equation. Okay, is it's only going to get you the speed. It's not going to get you the direction part. So if the direction of motion of the object is unknown, the equation cannot be applied. And when is that the case? Well, we can throw things downwards, but we can also throw things upwards. Okay, and unless we reach an escape velocity, what goes up must come down, in which case you have motion in two directions, which we'll focus on that a little bit later. Available on the Honors Physics Schoology group. Okay, there is a printable version of this. This is motion formula, so all the equations that we worked with as well as the timeless. The variables that appear in these equations are listed along this top column here. Okay, and so many students find this useful when they're learning how to apply these equations, to use this as like a cheat sheet. As you're reading through the problem, identify knowns and unknowns, okay, and then see which ones apply. So like the first question we solved today was about a rocket, where we were told how far it goes and how much time it takes, and we were asked to solve for the average velocity. So those three variables are there. So we'd use this formula, okay? Or we just solve this problem where we're given the ball is dropped. Okay, we want to know how fast it's going when it falls from displacement, and the acceleration is gravity. Hey, why not go and use the timeless equation? Okay, so it's a good little teaching tool for yourself. So I encourage you to get your hands on that and use it as you are moving through solving physics problems in motion. All right, so this is Mr. Zarzak saying thanks for watching, and we will see you next time.